Next question 4. F is twice continuously differentiable on the unit disk because we are considering two-dimensional space. B1 is B12, two-dimensional ball, and the F satisfies the equation. F satisfies this equation in this ball, in this unit disk. So we want to prove that x plus, we want to prove that this is pi over 2e. This is the question. So this is the unit disk, the B1. We want to prove this. How to solve this problem? This problem has many different methods, but I can only talk about one of these. So the key point is that to observe that x df dx plus y df dy, this can be considered as xy, then inner product with the gradient of f. This is the point. So why we want this? Because we have the Green first identity. We just in our previous example, we also depend on the first Green identity. So the first Green identity says that omega gradient of v u gradient of v plus u Laplacian of v is the surface integral okay. So compare the Green first identity and this expression. We want to find a function. We want to find a function such that it is. We want to find a function u such that what? Such that the gradient of u is x and y. When we do this, because we want to substituting v for f in the first Green identity, then Laplacian v here, the Laplacian v is a result we know. If we apply the Green identity for the unknown u and v equal to f, then the Laplacian of v is known. Laplacian of v satisfies this condition. Laplacian of v, that is f, is exponential of minus x squared plus y squared. It is a known function. Okay, so we want to find a u have this property, but even if you find such a u, let's go back to the first Green identity, the right hand side. The right hand side, you still need to compute u multiply the integral of u multiplying the directional derivative of v, that is f, over the unit sphere. So can we eliminate this term? Of course, if the u is 0 on the unit sphere, we also require u is 0 on the unit sphere. If you can find the function u having these two properties, the first property is that its gradient is just xy, and it is 0 on the unit sphere. On the unit circle, because we are two-dimensional problem. Okay, if you have such a u, then we can apply the first Green identity. Okay, is there such a U? Yes. The answer is yes. Because gradient of U is xy means that ux is x, uy is y. Obviously, you can try this function uxy to be x squared plus y squared over 2. Then it satisfies ux, the partial derivative which x is x, which respect to y is y. But this function does not satisfy our another requirement that it is 0 on the unit sphere. But this is easy. You just modify this u, substituting a half. On the unit sphere, on the unit circle, x squared plus y squared is 1. So after subtracting a half to our previous u, the new u will satisfy all our requirement. Okay? So this is the idea for solving this problem. Therefore, we lack applying Green first identity to u equal x squared plus y squared minus 1 over 2, and v is f. We get x plus u Laplacian of f, because this term is just gradient of u, gradient of f. Okay, so this will be the boundary u. The boundary of B is the circle, so this is a line integral. The line integral is 0 because u is 0 on the unit circle. Okay, so we obtained that the integral we are studying is minus u Laplacian f. Okay, then this is our condition is that Laplacian f is exponential of minus x squared plus y squared. Okay, so that is minus u is a half of x squared plus y squared minus 1. This is u. Laplacian f is exponential minus x squared plus y squared. Then dx dy. Of course, this integral is easy to compute because the B is the unit disk. So you can use the polar coordinate minus 0 to 1 dr, maybe 0 to 2 pi d theta, 0 to 1 r squared minus 1 over 2 exponential of minus r squared, then r dr. So this is 2 pi 1 minus r squared 2 exponential r squared r dr. This term, because of the minus sign here, so this becomes 1 minus r squared. Okay, so this integral can be computed, not difficult, and the result would be pi over 2e. Okay, so this proves our deserved result. So the key point here is to apply the first Green identity as what we did in the previous example. And but how could you think of Green's first identity? So this is the crucial inspiration, because the integrand on the integral we are studying is precisely, we consider this as the inner product of the gradient of f, which is something, And if that something can be written by the gradient of some function, then we can try first gradient identity. Okay. The problem phi requires some long discussion, so we consider a simpler question, the sixth question. F is continuous. And phi is a curve, closed curve in R2. Smooth and closed path. Then we are required to solve that this integral. So this integral is of this form: p dx plus q dy over a curve, over a path. So this is a flow integral. Okay, this is what we say flow integral. So it is very natural to consider apply the Green formula, because Green formula concerns a flow integral of this form over a closed path. But I will say here is a closed path. So we can try Green's theorem. That is the boundary of omega p dx plus q dy equal okay, this is a natural idea, right? So we apply this Green formula for p to be xf x squared plus y squared, and for q to be y f x squared plus y squared. Therefore, the qx, what's wrong? The qx minus the py, what's this? The derivative of q with respect to x is y f prime x squared plus y squared. Then multiplying the partial derivative of x squared plus y squared with respect to x, that is 2x. Okay? Then minus the partial derivative of y of p with respect to y, that is x f prime x squared plus y squared. Then the partial derivative of x squared plus y squared with respect to y, that is this 2y. Of course, the result is 0. So our f x squared plus y squared x dx plus y dy is just the same p dx plus q dy. This will equal the integral of qx minus py over the omega. Omega is the domain bounded by C. Okay? You take omega to be the domain in the plane bounded by the closed path, that is C. Then C is the boundary of omega, so we can apply the Green theorem. And the integral we have just computed that the integral is 0, therefore the result is 0. Okay, so this seems to be a very good proof of our question. Unfortunately, this argument is has some serious problem. Because what? Because we have used the derivative of f. Okay, but our f is only continuous. We don't know whether f is differentiable. F is only a continuous function. You could not write the derivative of f. Okay, this is the first problem. The second problem is that C is a closed patch, but closed patch does not mean that it is a boundary of a domain. For example, C can be of this form, or C can be then go there. C can be sine curve in this form, so you cannot say the omega is the domain. You cannot require omega to be the domain bounded by C. You cannot say this. Of course, this is the most crucial problem is that our f is only continuous, not differentiable. So this is the problem of this proof. We will give a correct proof in the next video.